All right, so let's pick up with number 33. We want to identify the conjugate pair needed to comprise a buffer solution. So remember that a buffer solution is a weak acid and its conjugate salt, or a weak base and its conjugate salt. The only answer choice that meets both those criteria would be C. NH3 and NH4Cl. The Cl is really a counterion, so it's NH3 and NH4 plus. So number 33, the best answer is C. If you have a solution that's saturated with AgCl, this is going to be the common ion effect. So if we have AgCl, that's going to be in equilibrium with its dissociation. Of course, that's governed by KSP. And we'll have Ag plus that's solvated, and we will have Cl minus that's solvated. If we add HCl, we're going to increase the concentration of Cl minus. And by Le Chatelier's principle, we will see a shift to the left, and so we will dissolve less. That means we'll have less Ag plus in solution, and we'll have less Cl minus in solution. And so this will decrease the concentration of solvated silver ion. So number 34, the best answer is B. How many moles of electrons are transferred in this process? We actually did this reaction earlier, and we found that 6 moles of electrons were transferred. So you may want to refer back to the previous screencast. I believe it was question number 25. Actually, we can check that real quick. We dealt with this. Number 26. So if you look at number 26 in the previous podcast, I worked the whole problem out, and it is 6 moles of electrons. Number 36, if I change the pH by 3 log orders, so that pH goes up, that means hydronium goes down by a factor of 1,000. So that would be choice D. 37, a very typical Faraday's Law problem, so let's take a look at this one. Certainly one I would expect to see on final. And so we're going to go 1.20 minutes. We know that 1 minute is 60 seconds, and we need it in seconds because current is in amps, but that's a coulomb per second. So we have 35.2 coulombs per second. Seconds, of course, cancel. We have 96,485 coulombs per mole of electrons. Coulombs cancel. 2 moles of electrons are needed to reduce 1 mole or produce 1 mole of iron. And 1 mole of iron is 55.85 grams of iron. And we're left with grams of iron, which is precisely what we want. So now it's a matter of simplification. 11.2 times 60 times 35.2 times 55.85. And we're going to divide this by 2 and then by 96,485. And I obtain an answer of 6.83 grams, which is credited response C. So number 37, the credited response is C. All right, so 38 through 40 refer to the following equilibrium. 38 asks, this reaction would be predicted to be spontaneous under what conditions? Certainly it is going to be entropically favored, but it is going to be endothermic because you're breaking a bond. Therefore, it would be spontaneous at very high temperatures. So that should correspond to choice D. The change in enthalpy is going to be negative because bonds are broken. That's choice B. And the change of entropy in the system is positive because there are more moles of gas in products than reactants. That answer is C. Number 41, we have an equilibrium constant that is much, much greater than 1. That means you have a spontaneous reaction, but it tells us nothing about the rate. So we know that it's spontaneous, but we do not know if it's instantaneous. It could be fast, it could be slow. Number 42, we have the decay of polonium-214. Remember, polonium was discovered by Marie Curie and it was named for her native Poland. And polonium consists of decay from an alpha particle and then 2 beta particles. And then finally another alpha particle. So the mass number changes by 2. So we'll have lead for sure. So you can use that to get rid of A and B and E. And the atomic mass is going to go down by 8. This is the familiar lead-206. This is answer choice C for number 42. 42, the credited response is C. Radioactive decay. If I go from carbon 14 to nitrogen 14, we actually talked about this in the review today. This is beta particle emission, so that all of the numbers balance. 7 minus 1 is 6. So you are releasing a beta particle or an electron. So the best answer is going to be A, beta particle emission. So let's move to number 44. And I think I'm just going to try and tie up all of these problems. We have another radioactive decay problem. Notice that we will have 133. So 251 minus 133 is going to be, looks like about 118. Once you find that it's 118, you're really done because you can get rid of A and C and D. And for number 44, the credited response will be B. If I go from 1 atmosphere to 0.125, notice very carefully, this is not a difficult problem, but most people make it really difficult. If I'll go from 1 to 0.5 in 1 half-life, then to 0.25 in 2 half-lives, and then to 0.125 in 3 half-lives. Each half-life is 19 minutes. So 19 times 3 will be 57. 57 minutes. That is answer choice B. B is the credited response for number 45. Number 46, a little bit different. We are going to only have 12.5% of what I once had after 24 days. We really just saw this math. We'll do it in a different way. So if I start with 100%, after 1 half-life I'll have 50, after 2 half-lives I'll have 25, after 3 half-lives I'll have 12.5. That means I have 50% decomposed, then 75% decomposed, than 87.5% decomposed. 3 half-lives are 24 days. Half-life of iodine-131 is 8 days. Very well-known result because we use iodine to detect thyroid pathology, either tumors or hyper or hypothyroidism. So for number 46, the best answer is B, 8 days. All right, so 47 is going to be very similar to 44. In 47, we'll just map this out for a moment. Need a new sheet. So we have 235 uranium, and we have a neutron. We have 141 cesium. We have 3 neutrons. I'm going to write this just a little different. Because there's 3 of them, that's a mass of 3. And I'm going to have X. 236 minus 144 will be 92. Minus 55 will be 37. Element 37 is rubidium. This is choice D for number 47. So for 47, the credited response is D. All right, 48. We have a weak acid, HA. It's 0.2 molar. Of course, we know when it dissociates, it has a pH of 3, which means the hydronium ion concentration is 10 to the minus 3. So that means 10 to the minus 3 squared divided by 0.2 is equal to the Ka. That is going to be 5 times 10 to the minus 6. And so that is choice C. Number 48, the credited response is C. We want the equilibrium constant for this Nernst equation. And so the best way to do this is probably to look at some mathematical correlations. We know delta G is minus RT log of K. We also know it's minus NFE. So minus RT log of K equals minus NFE. K equals E to the NFE divided by RT. And now it's just a plug and chug problem. You have 2 moles of electrons. You have 96,485. The E for the reaction is going to be 0.21. And you know this because iron must be oxidized. This shows the reduction of iron 2+, so we need to flip this around and add them together. So plus 0.44 plus minus 0.23 is plus 0.21. R, of course, is going to be 8.3145, and our temperature will be 298 Kelvin. So first I would find what the exponent is going to be. So we have 2 times 96,485 times 0.21 divided by 8.3145 divided by 298. So that power is 16.355. So now I'm going to take the base E of that value, and I get 1.26 times 10 to the 7th, it looks like. So that's going to be answer choice D. Number 49, the credited response is D. Which leaves us with, can I get a drum roll please, number 50. And 50 tells us the solubility of CuI is 2 times 10 to the minus 6 molar. CuI goes to Cu plus and I minus. If this is 2 times 10 to the minus 6, then so are these. And so I just need to square that value. That'll be 4 times 10 to the minus 12. So number 50, the credited response, is also C. And that concludes the mock test solutions for the second semester exam 3.